Hi, welcome to Modern Optimization Methods. Today we will introduce the fourth part of Chapter 6, Semi-smooth Newton's method applied to support vector machine. Now, let's recall that support vector machine is divided into support vector classification and support vector regression. We mainly focus on the L2 loss SVC and epsilon L2 loss SVR, the two types of SVM method. In the following, we will take the L2 SVC to demonstrate how we apply semi-smooth Newton's method to solve the problem. Okay, so now the first thing we do is that we add the variable x to one dimensional. Okay, so we set x as x1, so we add one dimensional to the observation x. And then the variable we are looking for, the omega, also we have one extra component as omega b. Okay, in other words, we take omega b as one vector and we solve the problem. By doing this transformation, then we can put L2 loss SVC into the following form, where we also minimize the square norm of omega and also a loss function, the L2 loss function. Okay? So after we rearranging into the following form, next we need to take a look at the epsilon L2 loss SVR model. We do similar strategy to reformulate it into the following form. Okay, so basically we put those b variable into omega and then there is only one variable left. Okay, however, the dimension is increases to Rn plus 1. Now, if we take a look at the two problem, we do not introduce more variables to rearrange it into a constraint problem. We just take a look at this unconstrained optimization model. Okay, so is it possible that we solve the problem directly? All right, so this is the question we ask. Actually, if we analyze the dimension of this problem, we can see that the benefit of the problem is that it is unconstrained. And there is only one variable omega in this problem. Okay, there is no constraint and there is no other variables. Okay, so it is a very neat form of the problem. Moreover, if we take a look at the property of this function, f1 and f2 omega, both of the two functions, they are continuously differentiable. In other words, we can take gradient to get the gradient of the two problems. Okay? However, after we taking gradient, we cannot take the Hessian matrix at all because the problem is not twice continuously differentiable. All right? So this looks like a bad news. Okay? However, we can make use of this non-differentiable property by using semi-smooth Newton's method. Okay, so this is the idea. Now, let's take a look at the SVC problem. So solving the L2 loss SVC is equivalent to solving the first order optimality condition, which means the gradient to be 0. Okay, so this is a nonlinear system, and we try to solve this. We can write down the gradient in an explicit form, like this. Okay, we just do the chain rule to get the gradient. All right? And notice that in this gradient, the first term is omega, which is nice, and the second term, you can see that there is a max function inside it. Okay? It is a sum of each max item. So this brings a very interesting difficulty. We cannot take further Hessian matrix. However, this gradient matrix, it is strongly semi-smooth. All right? So strongly semi-smooth, as we mentioned before, the max function is strongly semi-smooth. And there is some sum of the max function, and also we have some multiplication of the max function, right? So as we mentioned, any composition of strongly semi-smooth function, it is strongly semi-smooth, okay? Therefore, the gradient function here, it is strongly semi-smooth. In other words, this nonlinear function, we got this nonlinear function, it is actually strongly semi-smooth. So we can use the semi-smooth Newton's function. Okay? We apply the semi-smooth Newton's function to solve this nonlinear system. So this is the idea. Now, next, the only key point we need to fix is, can we characterize the generalized Jacobian of the gradient? Okay? So to characterize the generalized Jacobian, we need some tools. For example, we need some chain rules and also some theoretical knowledge about how we characterize this generalized Jacobian. One thing is that for the composition of two functions or many functions, the generalized Jacobian of this function f1, we cannot characterize it directly. However, we can characterize a bigger set which contains this generalized Jacobian set. Okay? So this bigger set is expressed as this. This is what we proved, okay? We proved that this V1 takes the following form. In other words, if we can characterize a bigger set like this, then when we apply semi-smooth Newton's method, we just pick up elements from this set, okay? So this is the idea. And here, notice that for the set V1, we also got some sum here and a coefficient h, where this h is actually from the generalized gradient of max function, okay? In other words, due to different values of zi omega, this hi will have different values. So as we mentioned in the previous chapter, if this variable zi omega is positive, then h will be 1. If it is negative, h will be 0. If it is 0, then hi lies in the set between 0 and 1, okay? So this is the generalized gradient of max function. So as a result, due to different choices of hi, V1 may have different elements in it, okay? So the thing we need to do is that when we update semi-smooth Newton's method, we choose one particular element from this capital V1 based on different choices of h, okay? Then we apply the globalized version of semi-smooth Newton's method. Now, let's consider the global and local convergence of semi-smooth Newton's method when we apply it to solve the SVC problem, okay? So for local convergence rate, as you may recall that to guarantee the local convergence rate, we need two properties. One is the strongly semi-smoothness of the nonlinear function, okay? The other is the non-singularity of elements in the generalized Jacobian set. So let's verify them one by one. So for the semi-smoothness, we can already show that the gradient function is strongly semi-smooth, okay? So this satisfies the first condition. And for the second one, we can actually show that this matrix, any matrix V in the capital V1, it is all of them are positive definite. Okay, so positive definite, of course, it is non-singular, all right? In a word, the two conditions for convergence rate are already satisfied. Therefore, we can guarantee that when we apply semi-smooth Newton's method to solve SVC problem, we can get quadratic convergence rate, okay, which is very nice. And now, let's make a brief summary about this part. We actually apply semi-smooth Newton's method to SVC and SVR problem. When we apply to SVC problem, we can get quadratic convergence rate. And notice that we applied the globalized version of semi-smooth Newton's method. Therefore, the global convergence result can also be obtained. For the SVC and SVR problem, we can all get the result of global convergence and quadratic convergence rate. Okay? More numerical results will be detailed in next part. So we stop here and see you next time.